Alright, so in this video I'm going to be explaining this important article which has been the motivation of many researchers in the field of geometric deep learning. And so this paper in 2021 from Professor Max Welling in Amsterdam. This paper introduces a new model to learn graph neural network equivariant to rotations, translations, reflections, and permutations, called E of n equivariant graph neural networks. In contrast with existing methods, our work does not require computationally expensive higher order representations in intermediate layers, while it still achieves competitive or better performance. In addition, whereas existing methods are limited to equivariance and three-dimensional spaces, our model is easily scaled to higher dimensional spaces. We demonstrate the effectiveness of our method on dynamical system modeling, representing learning in graph autoencoders, and predicting molecular properties. For example, a molecule, these are atoms of that. All of these have some distances and angles, and so it's a highly geometric things. So it's a kind of geometric graph. And here is an example of rotation equivariance on a graph with a graph neural network. You see, if we do the group transformation and then do the transformation, the graph neural network update is the same as first graph neural network update and then transformation. So this always holds. This equivariance property always holds, that we can interchange it. And then, so for graph neural networks, we can generalize it to message passing, and then that graph neural networks are permutation equivariant networks that operate on graph structured data. So given a graph with nodes v sub I and edges ei, e sub ij, we define graph convolutional neural networks that was first defined in 2017 like this. And n sub I, is just a set of neighbors of node I. And finally, phi sub e and phi sub h are the edge and node operation respectively, which are commonly approximated by multi-layer perceptrons. But what is this equivariant version of graph neural network? Our equivariant graph convolutional layer takes as input the set of embeddings, coordinate embeddings, and edge information, and outputs a transformation. Concisely, we can write it like this. So not only edge is updated, but also the coordinates are updated. So in layer L, we have this coordinate, but in layer L plus 1, it is updated like this. So this is the extra thing that we should know. We are also updating the coordinates, because a linear combination of coordinates, the distance between the coordinates and their representations is m. So the coordinate representation comes here and is updated. So the next representation in the next layer is also influenced by the coordinates, the distance between nodes, and all geometric things. And they mentioned that the main difference between the above proposed method and the original graph neural network is just equation 3 and 4. In equation 3 here, we now input the relative squared distance between two coordinates into edge operation. The embedding h sub I, h sub j, and edge attributes, so these are edge attributes, like, for example, anything that you can imagine, geometric thing. And then the embeddings also provided an input to the edge operation. So in equation 4, in this equation, we update the position of each particle as a vector field in a radial direction. In other words, the position of each particle is updated by the weighted sum of all relative differences. And now they are working on the analysis of that. Our model should be translation equivariant on X. So let's see if it is equivariant or not. And it should also be rotation and reflection equivariant on X for any orthogonal matrix Q. So let's make it happen. So they provide the proof here that it makes sense that they are equivariant. If you just work on this equation and simplify it, you will see that the equivariance relation holds. Now in this section, they are extending this equivariant version of graph neural network for vector type representation. Slight modification to the presented method such that we explicitly keep track of the particle's momentum. So it's not just the position, the coordinate, but also the position, the momentum of that as well. So the momentum, the velocity momentum is just updated based on initial momentum. So instead of just edge and position, we also have this momentum to update the momentum as well. Because not only we update the position, but also we update the momentum. We may not always be provided with an adjacency matrix. In those cases, we can assume a fully connected graph where all nodes exchange messages with each other. This fully connected approach may not scale well to large point clouds where we may want to locally limit the exchange of messages. So we present a simple solution to infer the relation or edges of the graph in our model, even when they are not explicitly provided. Given a set of neighbors of each node, we can rewrite the aggregation operation from our model in this form. So E takes value 1 if there is an edge between nodes. Now we can choose to approximate the relations E sub ij by this function that resembles a linear layer followed by a sigmoid function that takes as input the current edge embedding and outputs a soft estimation of its edge value. So this is the comparison over different works from the literature on their message passing framework. We created this table with the aim to provide a clear and simple way to compare over these different methods. The names from left to right are graph neural networks, radial field equivariant flows, tensor field networks, and equivariant graph neural networks. So we proved that our model is, as I said, they have proved it in the appendix, that it is translation equivariant for any translation vector G. For any translation equivariant vector G. So let's carry on. We've proved the model satisfies this. We will analyze how a translation and rotation of the input coordinates propagates through our model. If we start assuming H sub 0 is invariant to En transformations. So we do not encode any information about the absolute position or orientation. Then the output M sub ij will be invariant too, since the distance between two particles is invariant to translations. because G is just cancelled, and what remains is the invariant, and is invariant to rotations and reflections as well, because we have converted this one into this one. It shows that it is invariant. The second equation of 4 that updates the coordinate is E of n equivariant. So we prove its equivariance by showing that an E of n transformation of input leads to the same transformation of output. So m sub ij is already invariant as proven. And this is the derivation. Reformulation for velocity type inputs. We write down the transformation later and can take in a velocity input and output channels. Same for velocity, the momentum for velocity type inputs.